Electroscope. The electroscope measures electrical charge, both sign and magnitude. The conductor rod is insulated from the glass container. When the scope is neutral, the leaves hang down due to their own mass. Electroscopes can be charged by conduction or induction. Here's a picture of an antique electroscope from 1878. Charging by conduction. A neutral electroscope will become negatively charged when touched by a negatively charged object. Negative electrical charge will distribute across the electroscope, and the gold leaves will repel, since they have the same charge, and like charges repel. Right here, our electroscope is neutrally charged, and we're bringing in a negatively charged rod, so it has more electrons than it wants. All right, so here we have our negatively charged rod. It has too many electrons. So when it touches the neutral electroscope, some of those electrons move onto the electroscope. So now the electroscope has more electrons. The bar is moved away, and there's a net negative charge on the scope. Negative charge moved from the rod to the electroscope. Therefore, the rod has less negative charge on it now, and the gold leaves here repel, since those extra electrons moved all through the rod and the leaves, and now there's too many electrons down here. Therefore, these leaves will repel each other since they're both negatively charged. The leaves would also repel if the experiment had been done with a positively charged bar. A neutral electroscope can also be charged by induction. If a rod with a negative net charge is brought near a neutral electroscope, then the electrons in the electroscope are going to be pushed down into the leaves at the bottom, causing them to repel each other. If the rod is removed, the leaves will go back to their original positions. This induction is temporary, and no charge is transferred from the rod to the leaves. A similar effect is caused by a rod with a positive net charge. The leaves will again repel, since like charges repel. One more piece is needed to affect a longer lasting charge on the electroscope. The missing piece is a ground wire. A neutral electroscope is connected to the ground, and a negatively charged bar is brought near. Let's see what happens. Here you can see the ground wire acts as an escape route. So as this negatively charged rod comes closer, electrons in here don't only get pushed down to the bottom, they can actually leave entirely. So they leave, they go down into the ground. Electrons in the scope will be repelled out of the scope and into the ground. The scope will then have a positive net charge. As with charging a sphere by induction, note that the charge on the rod does not change. So here you can see the electrons have left, leaving behind positively charged leaves, which will repel each other. A similar effect occurs for a bar that has a net positive charge. So you bring a positively charged rod close, and it attracts electrons from the Earth up into the electroscope. So the scope will end up with a net negative charge, since we'll end up with too many electrons, so therefore there will be a net negative charge on the leaves and they will repel each other. Again, the charge on the rod does not change. If the charging bar is removed while the ground wire is still attached, the electrons will return either to the ground or to the leaves until they have a neutral charge and will fall back together. In order to leave the charge on the electroscope and keep the leaves separated, the ground must be removed before the charging bar is removed. The electrons will now have no place to go, and a net positive or negative charge will be left on the electroscope. When the leaves of the electroscope repel, there is a charge present. It could be positive or negative. The electroscope can also be used to find out the charge on the leaves. You can take an object known to be positive or negative, place it near the top of the scope, and watch the reaction. Here's a summary chart of what the electroscope's reaction means, but we're actually going to go through and figure these out in the questions that are following. Intuitively, it would seem that the further apart the leaves move, the greater the magnitude or size of the charge present. This is true, and the next section will talk about the force due to electric charges, which is responsible for the leaves moving against the forces of gravity and tension.